Oh, that one.
Hello, good morning. Fine, thank you. I haven't graded the midterm 2 yet. I started with another course and that was took much longer. Should have started earlier. But I do think I should be able to complete the grading surely by tomorrow, if not tonight itself. So before the next class for Any comments on the exam itself? If you guys remember after the previous?
No.
That's right. Okay. Any general comments in general? Anything? If not, we will be having the same thing. We have sort of finished 2 quarters of the course, so it will repeat. Like you can say, there are some 3 or 4 homeworks and an exam. 3 or 4 homeworks and exam. We'll have midterm 3 similarly, and the last one will be a final exam. The only difference will be that it will be cumulative. That's the only difference. After midterm 3, I will decide on dropping a homework or 2. Most probably 1 homework will be dropped, and more than 1 quizzes will be dropped. So if you have lost a lot of points on that, so that can upgrade your grades a little bit. Otherwise, most of it, most of your grades after I grade midterm 2 should be what should. That's a decent representation of what you can expect in the exam. Remember that the final exam is not highly weighted; it's only weighted very similar to the midterm exam itself. So realize that. Yeah, homework 7. This is not posted yet, so this is due on Monday. So this will be posted by today evening. Quiz is already posted, so you should be able to go ahead and do the quizzes. Homework a few hours with delay. There's a midterm, so that will be homework 8 and 9. We will fill it in as we go. Midterm 3 is on April 8th, and it's on Friday. And this is very far, but it's good to at least once write in between, because in the early part of the semester, the syllabus did not show up because the final exam dates are decided in the 4th week of the semester. So this has been decided for this course, and it is on May 2nd, Monday. 8:10 I will not keep writing final exam until we finish midterm 3. But if some of you guys could check on this, like you have to look into the chart and find out when exactly the final exam is, just to make sure I haven't made any error, that would help. So do cross check the final exam date. So that's what is coming of the plan for the semester. This is pretty much exactly halfway through the course. We have finished 8 weeks. We are in the 9th week. Typically, there are 16 weeks, including the exam week. So we are in the 9th week of the semester, if you want. So what we want to do today is talk about magnetic field. And we have already come across a magnetic field in the sense we have asked what is a force exerted by a magnetic field. But here we want to talk about how can you create magnetic field itself. Most commonly, we create magnetic field, at least on a daily basis, using magnets. But here we would like to talk about how are the magnets itself, deep inside, how are the magnetic fields generated. And we will see that it is eventually a moving charge that creates a magnetic field. So let's review a little here. I'll have a motivation. We talked about electric fields. And we talked about two charges. If you have charges Q1 and Q2, so that is a positive charge Q1. We said it creates an electric field everywhere around itself. So it creates electric field. Creates E, let's say. And once the charge has created an electric field, this electric field exerts a force on another charge Q2. And the force is given by charge Q2 times the electric field due to the first charge. Notice the logical conclusion here. Q1 does something and Q2 experiences the effect of that cause, if you want. Q1 is the cause and Q2 is the effect, and force is the manifestation of that process. What we have talked now, at least in the last week, we had classes. We talked about magnetic fields, but we did not talk about how the magnetic field is created. We said any moving charge. So instead of talking about charge Q2, we talk about Q2 and a moving charge. So we need to give it motion. So it has a velocity V2, and that's Q2. And you multiply that piece out there. So instead of talking about a charge, you talk about a moving charge, and that's Q2 times V2. And if there is a magnetic field, then we said that the magnetic force it experiences is, we did not really write it in terms of Q2 and V2, we did not put in subscripts, but the force will be moving charge in the presence of a magnetic field of the first moving. We will see that it is going to be a moving charge. So the question here is, there is some creation of magnetic field. So what creates this magnetic field? Here, electric field is created by a charge Q, and that was Coulomb's law. Like what created the electric field and what's the equation governing that? That was Coulomb's law. Here, it will be a moving charge. So this is Q1. So that's moving with velocity V1. So it's going to be Q1 times V1. That's your source of a magnetic field. And that's on what does it exert a force? That's also a moving charge. So a moving charge experiences a force in the presence of a magnetic field, and a moving charge also creates a magnetic field. So it's a cyclic process. You can also talk in terms of the reverse of this. This creates a magnetic field, and this experiences a force due to that. Any moving charge also can be thought of as a current. If you have a lot of moving charge, you say it's a flux of moving charges, and you associate the word current to that. So instead of talking about a charge, a single charge that is moving, you can talk about a flow of charges. And in that case, you would say this is I2, right? The current that's going through a wire times the length of the wire. Right, so that's pretty much an analog of the same situation. If you have a stream of charges, you say it's a current of a current carrying wire. And in that case, the force is, again, replace this with I2L2. So that's current times the length of the wire crossed with V1. So now we are pretending that this is a current carrying wire, right? So there's a lot of charges moving in there. Same thing here. What creates a magnetic field? It's going to be I1 times L1. So a current carrying wire is pretty much analogous to a moving charge. So that's going to be our goal. So the idea is, what is this, right? That's where we are in. We have already covered this. We have analyzed that part. We would like to talk about what creates a magnetic field. What creates an electric field? Let's quickly recapitulate that. So that's Coulomb's law. Coulomb's law told us what creates an electric field. Electric field due to a charge Q. So let's say this is E1. That's equal to 1 over 4 pi epsilon naught times Q1 over R squared. And because it's a vector, we also have to associate a vector nature to this, and that's R hat. And this is a symbol of a radially outward vector from Q1 to observation point. And you have used this sufficiently, so now hopefully it's clear what that R hat means. But the main content of this is in here. That's a magnitude, and that's the direction. And the direction, you write that as a symbolic representation. What is the law that tells us what is the magnetic field that is created by a moving charge, or for that matter, a current carrying wire? Remember that we never try to prove this, right? This is a law. This is an experimentally established law. We cannot prove that in a mathematical sense. Starting from something else, we cannot reach here. The best we could do is we could use Gauss's law and conclude some very generalities of this law, but otherwise we could never prove that. Same thing here. Magnetic fields now will be created by a law. It's Biot-Savart law. I think it is pronounced as Biot-Savart law, but I'm not very sure about that. Check on that. So what is the magnetic field created? So again, it's a vector. So that's V1. And whenever we have this Q, whenever I write Q times V, I can replace it with I times L. So that's the idea. And here, first of all, it is not the epsilon naught that shows up. That was the electric permittivity. So here there is a new constant, mu naught over 4 pi. The same 4 pi shows up, but instead of epsilon naught showing up in the denominator, there is a new parameter mu naught that comes in the numerator. So mu naught is permeability of vacuum. And remember epsilon, so you can say this is magnetic permeability of vacuum. Epsilon naught was permittivity of vacuum. So if you have nothing around, then what is the electric property of the material? If you have a material, then you say this is the electric property of the material itself that is coming in. So that's that first piece in there. That's just change. Instead of epsilon naught, we put in the magnetic property in there. Here it was Q1. We already noticed that wherever there is a charge, we have to talk about moving charge. So we have Q1 times V1. Or for that matter, I can write instead of Q1 times V1, I can write I1 times L1. And mostly we will work with the currents, so we want to change that very quickly. And rest everything remains the same. So that is an R square. And that is an R hat. Again, the same idea, radially outward vector from the instead of charge, it is that moving charge, and that is R hat. And you will notice that there is a small challenge here because these are two vectors and left hand side is a vector. How do you write two vectors in terms of a vector? But that's not something new. We already came across that, oh, this is a mistake, right? There shouldn't be a vector sign here. That's a charge. Charge is not a vector. That was a mistake, sorry. So it's charge times velocity times the magnetic field. And when you take this product, you do a vector product. The vector product of two vectors is a vector itself. And we saw that earlier. And the same thing here. Now it is a cross product. So we want to talk about what is the magnetic field created by a moving charge. So we have to take this cross product and divide it out by R square. And we will do some simple situations. Most of the time, this comes out very mathematically tedious. We will do some simple exercises in this case instead of talking about any general moving charge. Same thing here. Instead of a moving charge, if I have a current carrying wire, mu naught over 4 pi times I1 times L1 crossed with R hat over R square. Before I proceed, so we will do specific cases where an elementary piece of wire creates a magnetic field, then we will be able to do various configurations using that. But before that, I should point out what is mu naught, right? So that is epsilon naught was played an important role in Coulomb's law. What is permeability due to vacuum? What is the expression for that? So mu naught is equal to 4 pi into 10 raised to -7. And it has units. So now, in this case, the units can be deciphered from here itself. So that's magnetic field is in Tesla, meter squared, charge, and you can say this is current times length, right? So it is Tesla, meter over amp. Right, so that's the value for your mu naught. That is an interesting observation you can make here, and displayed a very this was displayed a very important role in the development of, if you want, light and radio waves. And the observation is the following: that now we have a magnetic property of a vacuum, and we already have the electric property of vacuum. What if we multiply these two quantities? So epsilon naught times mu naught. So let's just, for the sake of it, multiply these quantities. One is 8.85 into 10 raised to minus 12, and the other is 4. Actually, I should do inverse of this, but let's first do this. So that's 4 pi into 10 raised to minus 7. Once we have this number, we want to invert this 1 over epsilon naught mu naught, and then we want to also take the square root of this one. So first, let's calculate this number. So let me keep some more digits and I'll come back to that. So into 10 raised to minus 19. So that's 0.1112 into 10 raised to minus 16. So let me write that as and that comes out to be 1 divided by, and that's 2.99, at least to 3 sig digits into 10 raised to minus 10 raised to 8. Right, those are the numbers. So currently this just seems to be a number associated with some properties of vacuum. Remember, again, this is a property of vacuum. We are saying that when there is empty space, it has some general property associated with it and a numerical factor associated with it. And it should also have a unit, right? This has a unit, epsilon naught. Just for completeness, this is 8.85 into 10 raised to minus 12. And this was coming from Coulomb's law. So this will be, so that's Coulomb square, Newton meter square. These can be replaced with your force. There is already a force there. And if you do all the cancellation in there, this comes out to be second over meter and the square of that. And that's the reason why you invert it. If this units of this quantity is second square and meter square, if I were to invert this, let me write this again. That's second square meter square. This will be inverse of that, and then I took a square root. That's meters per second. So what we are talking about here is that there is some electrical property of empty space. There is a magnetic property of empty space. You multiply them together, and there is something with units of meters per second. And it doesn't take too much to realize that meters per second is the unit of speed. So whatever this is a property associated with empty space. And there is a velocity associated with it. So there is nothing moving when you're talking about empty space. The whole idea is that it's just sitting there, and this is a speed associated with empty space. And it turns out already this was realized in 1860s, and it was already known that speed of light has exactly this value. So this is speed of light in vacuum. Like speed of light changes from medium to medium. So the fastest is in vacuum. And it turns out very random, or completely remote concepts like electric property of vacuum and magnetic property of vacuum, when multiplied together in a certain way, gives you a speed which turns out to be the speed of light. And we will see that this is the first realization that light that we see around us is actually an electric, and is at a very fundamental level an electrical property, or has electrical properties and has magnetic properties. And we will come to that as we proceed further. So about 3 weeks down the line, we will see how exactly light can be represented in those terms. So this is just an observation that this is speed of light. In fact, now it has become so standard that instead of talking in terms of these two constants, in 2006, there was typically the values of these constants is decided by a committee that sits in a room and decides what is the most appropriate thing to do. So these days, C is considered a fundamental constant in the sense it is not derived, we associate a value to that. So C is associated or is given a whole number value, that's 299, 792, and 458. By whole number, I mean this is exact. There is no more decimals after this. This is a whole number, and that's speed of light. So this is just the first 3 significant digits of that. So that's speed of light. Mu naught, you decide as 4 pi into 10 raised to minus 7 Tesla meter over amp, and epsilon naught now is defined as, so you invert this whole thing. We derived C out of mu naught at epsilon naught, but now it is the inverse that works. You say this is the whole number, and whatever this comes out, so C will be equal to, or epsilon naught will be equal to mu naught times C squared. Oh, 1 over. So you multiply 2 C squares and then you multiply mu naught, and that's how you would define it. So that's an observation, but let's proceed with the magnetic field created by currents. We'll come back to this idea later on when we talk about the property of light. We want to use the idea of Biot-Savart law and do some examples. The simplest example will be a straight wire. So let's say finite straight current carrying wire. By wire, I mean there is a current I passing through. So it's a finite wire. So that's your current carrying wire. It has a finite length, and the arrow represents the direction of the current. So that is a current I flowing through this, and it is a finite length L associated with it. But instead of saying this is directly L, I'm going to split this into 2 pieces. So let's say there is an observation point somewhere here. And the way I have shown it, it's not symmetrically and it's not exactly at the center of the wire. Even if you draw a bisector to this line, it is not really on the bisector of that wire. So it is asymmetrically located. So that's your observation point. And we would like to now ask, what is the magnetic field at that observation point? So the formula for this, or the way to use Biot-Savart will be, is that have a perpendicular line from the observation point all the way to the wire. So that's this. That's a perpendicular line, and let's call that distance A, or let's say R. So that's your observation or distance R. Let's have this piece here L1 then, and this will be L2. But we will notice that it does not depend on. So the magnetic field, magnitude of this magnetic field, magnitude of the magnetic field created by this wire. So magnitude will be not having the direction associated with it. So we use this relation here. So that will be given by mu naught over 4 pi. Then there is the current I, that's I. It depends on how far you are. So it depends on this distance usually. That's R. It's a perpendicular distance from the observation point to the wire. And we will come across some special situations. What if this observation point is somewhere here? Even then you project this line downward and upward, and you have to draw it appropriately. We'll do some examples on that. So it's mu naught over 4 pi. It's proportional to the current. It is inversely proportional to the distance. Farther you go, it gets weaker. And now we have to get this asymmetry somehow. And that asymmetry is got by as a sine of the angle θ1 plus sine of the angle θ2. Now, what is the sine of the angle θ1 and θ2? This was the observation point. Again, draw a line extending all the way to the end of the wire. There are two ends of the wire, so there will be two such lines. And this angles θ1 and θ2 are measured with respect to that perpendicular line. And this is θ1, and that's θ2. Let me erase this. I have shown arrows here for θ1 and θ2, and that is important because that's the direction in which positive quantities are measured. For example, sometimes there will be situations where θ2 is measured downward, then you will put in the negative signs appropriately. So make sure θ1 and θ2 are measured positively in the arrow directions of the arrow shown. Otherwise, you have to put in negative signs to them. Again, I'll do some examples and hopefully that gets clarified. So that's your magnitude. What about the direction? So direction, if you want, you can call this the second right-hand rule. Already we have a first right-hand rule, so second, let's say. It's actually, if you, since everything comes out of this cross product, there is only one right-hand rule, and it is the same thing, but since or it's convenient to think of it as a second right-hand rule. It is easier to, as a student, it comes out easier. But at the origin, both are the same right-hand rule. So second right-hand rule. So what is the right-hand rule? So you use your right hand again, and you have a current carrying wire. The goal is to just hold it with the thumb pointing in the direction of the current. There is only two ways of holding the wire. Either you can hold it this way, or you can hold it this way. The thumb is pointing against the direction of current in the second way. So you hold it this way. So thumb is pointing in the direction of the current, and the curl of the fingers. So when you're holding it, there is a curl of your finger that gives you the direction of the magnetic field. So you have to look for the curl of the fingers, of the four fingers at this point. So if I'm holding this wire, the fingers are going into the board. So magnetic field is going in circles around the wire. So thumb is the direction of current, and fingers is B, the curl of the fingers. So what is the direction of the magnetic field? So that's your current. So everywhere the magnetic field is like this. So as you go farther, the magnetic field gets weaker. So this is at this point would be somewhere here. It's going into the board. So if you bring in the three-dimensional view to that, and everywhere. So if you have a point charge, you have electric fields coming out of the point charge. They're radially going outward. But magnetic field associated with a current carrying wire or a moving charge is the same thing. They are going in circle. They are circular lines, and they are going around it. If the charge is moving vertically up, then the magnetic field is going around it, and they do not start from a point. Electric field starts from a point charge, positive charge, and ends in a negative charge. Magnetic field does not start anywhere. It will always be in loops. Magnetic field, by definition, will always start and end at the same point. That means to say that they are complete circles. So they never start from a point. You will not. So for example, in principle, this is a three-dimensional diagram. So they have to come and connect together. They cannot originate from a point magically. So I'm just making that point clear, and you just close the loop. So magnetic field never start from a point. On the other hand, in contrast, electric field will always start from a point, from a positive charge, and end in a negative charge. So that's the basic idea of how magnetic field will be measured. But let's do examples. The easiest will be, let's take a very long wire, an infinitely long wire. What happens? For example, the infinitely long one, and we mean straight one. So how you represent that is the same piece of wire there, but now these 3 dots mean that they go all the way to positive infinity, and at the bottom it comes from somewhere very very far from the bottom, so that's negative infinity there. Let's say the observation point is somewhere here. At this point, when both sides is infinity, there is symmetry there, right? By construction, that is infinity. Sorry, there is symmetry there. So these two are equidistant in that sense. This is again perpendicular distance. Let's call this distance A. It is the same distance as R, but let's say this is a parameter A associated with it. Next, we want to talk about θ1. The θ1 and θ2 played an important role. So where is the angle? So we have to draw a line starting from this observation point to the tip of the wire. So the tip of the wire is at infinity. So how do we reach that? What is the angle? So this is pretty much parallel lines. We have to keep trying to reach that bottom. So I will have to draw that line, and it will keep almost go parallel to this. And that's your angle θ1. So that's 90 degrees. Same thing you do here. You're trying to reach the tip of the wire, but it is at infinity, so you go parallel. So that's 90 degrees again. So what's the magnetic field due to an infinitely long wire? So B, magnitude of that is mu0/4 pi times the current I divided by how far your observation point is. This is the observation point where your magnetic field is being measured. That's your distance A. And now sine of θ1, which is sine of 90, plus sine of 90. Right, that's your magnetic field due to an infinitely long wire. Sine of 90 is 1. This is also 1. 1 plus 1 is 2. That is a 4 there. So this is equal to mu0 I over 2 pi times A. That's an expression you will often see. Of sometimes you will write this as R instead of A. The magnetic field due to an infinitely long wire is proportional to the current and inversely proportional to the distance of the observation point. What about the direction? The direction is you're going, so again, you hold the wire with your thumb pointing in the direction of the current. On the right side, your fingers go into the board. So this is going into the board here. So that's the direction of B. On the other hand, if your observation point was exactly the same distance onto the left, it will be coming out of the board. So this is coming out of the board. So usually how you represent this is, so this is the infinitely long wire. On the right side, everywhere on the right side, the magnetic field is going into the board. So that's the direction of the magnetic field. These are circular lines, but they are going into the board as a cross section, and they are coming out of the board on the left side. They get weaker a little, so the intensity of this number of lines decreases. So I'm showing it a little farther out. So that's the magnetic field on the right side, and they get weaker, so that's farther out. And the field lines are coming out of the board on the left side. That's your B magnetic field line. Again, these are circular lines. So they go like this and come back in here. So they go like this and come back here. Right, so they're circular lines in that sense. Hopefully that's clear. And you have to extend these lines also. These are all circles. Having done this, let's actually also talk about a situation where this could be negative. So let's have a situation. So again, an example. Just to emphasize the fact that this angle has to be measured in the right direction. You could have a situation where that's your finite stretch of wire. It starts from here and it ends from here. That's not very realistic. How can you start a wire and end a wire in air? Typically, it is a loop, and this is a contribution from one loop or one part of the loop. And your observation point could be somewhere here. So that's your observation point. And now you stretch this wire out so that your line that is perpendicular to the wire comes out this way. So that's your distance A or R. And now the angle θ1. So θ1 is here. That's okay. That's our usual angle. So that's your θ1. But now θ2, notice, by definition there, it should have gone on the other side. θ2 is also in the same direction. So here θ2 should be negative. So this has to be taken care of, otherwise you start getting wrong answers contributing to that. We will now use this idea of a magnetic field due to a wire. Next time we will come and talk about a circle. So the three configurations you will need is a straight wire, a circular wire, and a coil. A coil is important because it creates a constant magnetic field. That will be called a solenoid. So we will talk about those in the next class. Thank you.
Yeah.
Again? I cannot understand you.
Tuesday.
Oh, yes, yes, sure. Yeah. Let's do that.